Hi, welcome back to Math 533, Topics in Euclidean Geometry. In this video, we're going to apply some of what we've done in order to solve some problems involving isometries. And the other thing we're going to do is we're going to develop a little bit of theory about compositions of various isometries. Okay, so let's start with our problem. This is a problem that I got from a book by Engel on math problems. The reference will be in the description box below. So here I start with a convex quadrilateral ABCD, and I am going to construct points M, N, O, and P as follows. So the first thing I want is triangles AMB, BNC, COD, and DPA to be equilateral triangles. And I want M to be on the same side of the line AB as C. N is opposite BC from A. O is on the same side of CD as A. And P is on the opposite side of AD from C. And then we want to show that the quadrilateral MNOP is a parallelogram. Now at first glance, this looks like some kind of alphabet soup. So instead of working with it without a picture, let's go ahead and take a look at a picture in GeoGebra. Let's illustrate the construction in our problem. So we start with this convex quadrilateral ABCD, and we now want to construct our points M, N, O, and P to make a bunch of equilateral triangles. Okay, so we can go ahead and use Euclid's construction to construct equilateral triangles with a given base. I'm instead going to use the GeoGebra built-in regular polygon tool. And that regular polygon tool is going to make things quite nice. So I want, right, so the first point I want to construct is M. So I need A, B, M to be an equilateral triangle. So M is either below the line AB or above the line AB. And we're told it's on the same side of AB as the point C. So I'm going to go ahead and construct my regular polygon with 3 vertices. Oh, I did it on the wrong side. Right, so if you use this regular polygon tool, you choose a vertex, the second vertex, and then it's going to make your third vertex going around counterclockwise. Okay, so this point is M. And now from N, I want N to be on the opposite side of BC from the point A. So N needs to be over to the left. So I'm going to go ahead and use my polygon tool to make the point E over here. Oh, I need to rename it. Sorry, that's the point N. So now O is on the same side as A, or the same side of CD. So it's on the it's above the line CD. So I'm going to go ahead and again use my regular polygon tool, and that point is O. And then finally I go, all right, I want my last point to be on the right because it's opposite from C. Okay, I need to zoom out a little bit. And this is the point P. And this is my picture. It's a very strange looking picture, but let's go ahead and we want to look at this polygon M, N, O, P. And that looks like a monochrome mess. So there we go. I've put it now in red, and the result we get definitely looks like a parallelogram, and here I'm moving my vertices around. And that's a very handsome looking parallelogram as I change where my points are. Okay, good. So that's what the problem is asking us to analyze. Okay, so now that we understand what the problem is asking us, let's do a little bit of a detour here on the side and talk about some important facts about angles and rotations. So we can define an orientation on the plane, and we want to think of that as being a direction, a preferred direction of a positive angle. So traditionally, we say that angles that rotate counterclockwise are rotating in the positive direction. So we'll continue with that standard. But it doesn't really matter. You just need to choose one and be consistent about it. Okay, so an orientation we think about as either, right, it's the distinction between clockwise and counterclockwise, or the distinction between positive and negative. We say an isometry is orientation preserving if it sends a positive rotation to a positive rotation, and that happens if it is a composition of an even number of reflections. And it's orientation reversing, so it sends clockwise to counterclockwise, if it is the composition of an odd number of reflections. Now, there's a secret theorem behind this assertion, which is that all of this makes sense and fits together in a coherent way. Once we have orientations, we can use them to define signed angles, or an oriented angle measure. So for this, I want to think now of the angle as being, well, an angle measure, for instance, in degrees, to be a number between 0 and 360. Right? Previously, we thought of our angles as being between 0 and 180 because we couldn't tell the difference between a clockwise angle and a counterclockwise angle. But here, because we have the orientation, we can tell them apart. So our angles, it makes sense to look at them going up to 180. Going up to 360. And I should point out, traditionally in Euclidean geometry, we don't think of signed angles or oriented angles. We usually think of them as unsigned angles and unoriented angles. And there's a good reason for that. And that is that our congruence criteria on triangles doesn't care about orientation. So if you think about our proof of the isosceles triangle theorem, right, we had this triangle ABC, and we flipped it over in order to show that the two base angles are congruent to each other. Well, that proof swaps the orientation of my triangle. It changes all the orientations around. So the angles are actually signed differently depending on which way we have it flipped. That doesn't matter for the purpose of congruence of triangles, which is why people normally don't think about this in the context of very classical Euclidean geometry. However, it's useful when we're talking about rotations, right? As we talked about it, a rotation cares whether you're rotating clockwise or counterclockwise. And a very nice fact is that if I take a rotation with the same, two rotations with the same center and angles theta and minus theta, then these two things are inverses, one from the other. Okay, so what happens if I take two rotations and I compose them? Right, we already saw what happened if we take two translations. Let's think about two rotations. So if I take two rotations with signed angles, so I call them capital theta 1, capital theta 2, and I have signed angles theta 1, theta 2, and I'm assuming they they have possibly different centers. Then the composition between the two, so theta 2 composed with theta 1, can be one of the following three things. I can get a rotation, I can get a translation, or I can get the identity. And so my three cases are if the angles don't add up to 360 degrees, or so they don't add up to 0 mod 360, then the rotation, the composition of the rotations is going to be yet another rotation with possibly a different center. If, however, the angles are opposite each other, so theta 1 and theta 2 are the same angle but in opposite directions, so in other words, they add up to 0, then the composition is going to be a translation if my two original rotations had different centers, and the composition will be the identity if they had the same center for both. Okay, we're not going to prove any of these assertions. Honestly, proving each of these three things is pretty straightforward, except it's kind of tedious and time-consuming, so we're going to skip over it. So let's jump back to our problem. So here I have ABCD is a convex quadrilateral, and I have my points M, N, O, and P as previously discussed. So now let's talk about strategy. What is a good proof strategy to solve this problem? Right, we want to show that the quadrilateral MNOP is a parallelogram. And the key idea we want to use is that a parallelogram and a pair of translations correspond to each other. So here we want to show that, let's say I have M, N, O, and P. I want this to be a parallelogram. Well, that means I can translate like so with a first translation. So I'm thinking of that as T1. And I can translate like so to give me my translation T2. Right? So in green here I have T1, and in purple here I have translations T2. So the idea is if I can find a pair of translations that send M and P to N and O, and then N and M to O and P, then I'm done. Right? That gives me a parallelogram by the various properties of translations. The other observation we have is that equilateral triangles have a rotational symmetry built into them. Now, we're not going to use the obvious rotational symmetry, which is the symmetry of rotating around the center of my equilateral triangle. Instead, we're going to use the observation that if I have an equilateral triangle here, let's say X, Y, Z, and I take a rotation centered at X, then if I choose the correct direction to rotate, so in this case, let's say I'm rotating clockwise, I send Z to Y by a rotation centered at X of angle 60 degrees. So here I'm leveraging a symmetry to say that there's a relationship between the points Z and Y, even though that rotation is not a symmetry of my triangle as a whole. Okay, so these are the two ideas we're going to leverage in our proof. Okay, so without loss of generality, my triangle ABCD is oriented positively. I introduce 4 rotations, each of them by 60 degrees, And for all of them, I'm going to take it to be a counterclockwise rotation, so a positive rotation. And I'm going to make the centers be A, B, C, and D, respectively. Now, the triangle AMB is equilateral, and because of where M is placed relative to A and B, I now have that if I rotate B in the counterclockwise direction centered at A, I get the point M. And if I take the point D and rotate it with A, I get the point B. Okay, so this one, I said here, since the triangle AMB is equilateral, here I'm using, let's say, and triangle APD is equilateral. Okay, so that's what I'm using to get this fact. Okay, so here I'm, just to illustrate the step, I have APD is an equilateral triangle, and I selected the wrong thing. I want also AMB is an equilateral triangle, so I'm going to make one of them is green and the other is purple. And let's think about these rotations, right? So if I rotate with a rotation centered at A, and I'm rotating in the positive direction, so in the counterclockwise direction, by 60 degrees, I send D to P in my green triangle. And also looking now in my purple triangle, I send B to M, right? So that gives me what I just claimed. And of course, we can repeat this argument looking at each of our triangles and each of the centers. So for instance, in my purple triangle, I can look at a rotation centered at B with where I'm rotating 60 degrees in the counterclockwise direction. That sends M to A. And if I look at a rotation centered at D, again rotating 60 degrees in the positive direction or the counterclockwise direction, it sends P to A. And then similarly working at the 4 rotations and looking at all 4 of my equilateral triangles, I get the following 8 identities. So the first 2 are the ones I just explained, and then we just go through and look at each of the vertices of our original quadrilateral. Okay, so that's maybe the hard part of this. Okay, and then now when I combine these observations, right, I can look, for instance, if I'm interested here in theta A inverse of M, well, from this up here, I have that right there is B. So I can replace it with a B, and then now I look at theta C of B, and that gives me N as the output. And then here, if I do theta A inverse of P, from that identity I get the point D, and then now I look at theta C of D, well, that gives me the point O. But by our observation that we just made a few moments ago, the composition of theta A inverse followed by theta C, that is a translation. I don't care what the vector of the translation is. It's just some kind of translation. And the reason is, right, this guy is a rotation by 60 degrees, and that guy is a rotation by minus 60 degrees, right? And we said opposite angles, the composition of these rotations gives me a translation if their centers are different. And in this case, their centers are indeed different. Okay, so that gives me a translation that sends m to n and p to o. We now want to look at the other way of translating these around. So here we're going to define a new translation here by looking at theta d inverse composed with theta b. Same kind of argument. T2 of m is p, T2 of n is o. And putting this all together, we have two translations, T1 and T2. The first translation, T1, sends m and p to n and o, and the second one sends m and n to p and o. And that's exactly what we needed to show that MNOP is a parallelogram. And that completes our proof. Right? That was a pretty involved argument, kind of messy, but it really leverages what we know about these isometries in a very fundamental way. Okay, that's it for this video. Thank you for watching. I hope you enjoyed this problem. I thought it was a lot of fun, and I'll see you on the next week. Thanks for watching. Happy mathing.